Okay. Welcome, PCS members and friends, to our today's PCS IBS seminar. It is a great pleasure to host today with us Professor Bilitewski from That's our usual echo. Our scientific host for today is Sergey, and please, Sergey, you can introduce our speaker.
Thanks, Steven. So welcome everyone to this, I hope, exciting seminar by Professor Thomas Bilitewski. Thomas did his PhD at the University of Cambridge with Nigel Cooper, which he finished in 2016. Then he moved on to the Max Planck Institute for Physics of Complex Systems, where he worked with Roderich Messmer until 2019. And then he moved from there to GMAT at the University of Colorado, Boulder, where he was holding a director's postdoctoral fellowship, which I guess is one of the prestigious fellowships, similar also to, well, I know the Los Alamos National Lab also has similar types of distinguished fellowships. So he had this one at the University of Colorado. And since, I think, this year, very recently, August or September, he moved to Oklahoma State University in Stillwater, where he is now an assistant professor. Congrats to that. And he visited us also as a speaker at the Dynamic Days Asia Pacific last week. And we are happy that he could stay for another week with us and talk with members of the center and explore possible interesting maybe collaborations or projects. We think there's quite some overlap in some of our research activities. Today, he will talk about long range dipolar interactions. Thomas.
Thank you so much, Sergey. Thank you for the invitation. And thank you for giving me the opportunity to be here for our week, talk to lots of people, interesting discussions, and I hope kind of some projects will come out of that. So since I talked last week about the classical spin physics stuff, I'm going to talk about something completely different today. But I just want to briefly kind of advertise maybe some things where there might be overlap with some things that people do here. So just a brief advertisement of other things I've done that I will not mention at all in the rest of the talk. So I did kind of a bit of classical spin physics, both in terms of kind of computing chaos out of time world correlate functions in these classical spin systems, in terms of both autocs and phase transitions. I talked about the hydrodynamics and KPZ scaling last week. And then I also did kind of spin systems, gem spin liquids, disordered spin systems. And out of that project, we also had kind of disordered flat bands on Kagome, which some people here also work on. So kind of that's other things I did at some point. Not going to mention any of that for the rest of the talk. So this is mainly classical. Everything else will now be quantum or semi-classical. And I will give kind of a very broad introduction. So if it's too basic and people are bored by these most basic motivational introductions, please tell me. I'm happy to skip over large parts of it, but I thought it might not be something that people here are super familiar with. So I wanted to give a rather broad introduction into the topic first. So maybe let me talk about why I like also doing kind of AMO, ultra-cold atomic systems. So one of the reasons why I like them is that they are perfectly controllable quantum systems in the sense that we can really look at the microscopic constituents and control them at that level. We can control the actions and the geometry and the temperature very, very well. And one of the applications that are pretty interesting is that we can then also use them for, say, sensing or, say, for atomic clocks. On the other hand, so for me, why I'm interested in them is I'm originally from the quantum matter context. So it's really about getting simple rules from complex behavior or getting complex behavior from simple rules, which is kind of what physics is about, in my opinion. And there's many examples of that in nature, of course. There's kind of pattern formation in the sense of, say, sentience. There's kind of swarm formation, kind of active matter. There's kind of behavior like fireflies, that they kind of all synchronize due to their actions. And most generically, you could ask about your networks that also have interactions or connections between them. And all of them, I would say from my naive picture, are quantum matter systems where interactions really make a difference than individual particles. And that's kind of, I guess, what Anderson originally kind of phrased, kind of behavior of a piece of matter is not just the sum of its part. It's really about the interactions that make kind of what we are doing interesting. And then to give you a brief overview to why are cold quantum gases pretty cool. So as I said, they are really cold, so you can control the temperature to a point where quantum behavior becomes important. You can also kind of choose what kind of particles you put in there, so you can have kind of multiple internal states, and we can choose how many there are and how they're coupled. We can not only control internal degrees of freedom, but also motional degrees of freedom by, say, combining them in certain potentials. We can control the dimensionalities from 1D, 2D to 3D. We can control the interaction graph of all these particles. We can even control the statistics of these particles, either bosons, fermions, potentially even anyons, and we can also have mixtures of those. And then finally, we can look at different things from atoms. We can also look at molecules. And that's something that I'm going to talk about in this talk. So the idea will be to kind of take some of these building blocks and kind of get interesting physics by combining some of these parts. So the next part of this talk will be about long-range interactions, and there's a few platforms where you can get them. So you can get them in polar molecules, you can get them in alkaline earth atoms, in trapped ions, in Rydberg atoms, or magnetic atoms. And I will focus on two of those, specifically polar molecules and alkaline earth atoms. So these are the two kind of platforms, experimental platforms that I will discuss in my talk. So the first part will be about polar molecules, and the very end will be about alkaline earth atoms. And then if I have a bit more time in the outlook, a bit more on polar molecules. So why are polar molecules interesting and complex? So first of all, they have strong dipolar interactions. So a polar molecule, or a heteronuclear molecule, is just a molecule that consists of two atoms. It kind of has a dipole moment because they're not the same, and that gives you rotational degree of freedom, and they can exchange dipolar quanta, which then gives you long-range dipole interactions. In addition, they are complex in the sense that they have a large internal state space that you can control. So specifically, experimentalists can do it via electric fields. And then they're useful for a variety of applications. So you can use them for quantum simulations. They kind of ask what is the quantum behavior of this system of quantum particles with long-range interactions. You can use them for quantum computing. There's actually a few companies that now try to do that commercially. You could be interested in ultra-cold quantum chemistry, which I will not talk about at all. And of course, for precision measurements, where you want to use the kind of the quantumness, the entanglement between particles to make something better than a classical sensor. So why are they complex? So one of the main reasons is why they are very complex is that the degrees of freedom span about 10 orders of magnitude. So if you go down to the binding energy of this molecule, you are about by 10 to 4 Kelvin, and then you go up to the motional 10 to minus 7 Kelvin. And in principle, if you want to use those for anything, you have to control this complex system over the whole range of all degrees of freedom, which then meant in practice that experimentalists had to do a very hard job to get new cooling schemes, and you needed to control chemistry losses. And that's why it actually took a long time to do this. Specifically, there's kind of the rough pictures. In 1995, we had atomic BCs, which you all might know. And it took about 25 more years until we had the degenerate gas of polar molecules. So there was a lot of work experimentally involved that I don't want to discuss here in detail. So all I want to say is now we have really fully controllable gases of dipolar molecules. And then give you a brief introduction about the basic physics of those. So I told you it's a polar molecule, so there's a rotational degree of freedom. So the basic Hamiltonian you might all know is a rigid rotor. So that's the basic Hamiltonian. You might all know that the basic eigenstates are just the angular momentum eigenstates that we all know for basic quantum mechanics. So specifically, I will look at the two lowest manifolds. So there will be ground state that is unique, and there will be a first excited level that is free. And we will apply electric field to split those, and then we can define a spin degree of freedom. So the basic building block will be that there is a down degree of spin degree of freedom and up degree of spin degree of freedom in these polar molecules. And that's what I will use them for mainly. And then the interactions are given by the dipole moments, which in principle are also field dependent. And we have these three different transition dipole moments, the transition dipole moment that is up and down states, and the field induced direct dipole moments. And then we get the interaction. So that's kind of the interesting part. So you have not only a single molecule, but they have two of them. They interact via these long-range dipole interactions. This is kind of the most generic form of this interaction Hamiltonian. The important thing is that it's a 1 over cubed interaction, so it's long range. And then these dipole moments have this anisotropic part, which comes from the projection of the dipole moment on the axis connecting the two molecules. And you can rewrite that by looking only at the one that preserves the total angular momentum of the system. And then you can pull out explicitly this vector into your cosine square term. You still have the dipole interactions, and you get a spin exchange term, and you get an Ising DZ term. And that's kind of the basic spin physics of this system. And they are anisotropic in the sense that if you put many molecules side by side, they will be repulsive. If you put them head to tail, they will be attractive. So the geometry of the system will kind of change what kind of interactions you can get. So you can already see that there's kind of potentially rich physics here, depending on how you choose the axis of your dipoles compared to the geometry of your system that you could play with. So this is still the kind of full dipolar Hamiltonian, and we now want to get to a magnetic system, kind of project it a bit further. So I told you we have a down-up degree of spin degree of freedom, and the idea will now be to take this Hamiltonian, project even further to a simpler system. Then you get a normal spin model that might all be familiar with. So after all of that, we now have a nice XXC Hamiltonian, where we have this anisotropic part, we have the 1/r cubed long range part, and we have an exchange J-perp term and an Ising JZ term. And in principle, all of these numbers can be tuned by using the electric field or the axis of the applied electric field compared to the geometry of your system. So the point is essentially a fully tunable XXC quantum model after the experimentalists did all the hard work to get here. So as I said, this J-perp term is directly this transition dipole moment, and the GZ term comes from the difference in the field-induced dipole moments of the up and down state. And the basic physics is just, if you have two of them, you have the spin exchange, which is induced by the J-perp term, and this just exchanges spin degrees of freedom. So you can kind of flip-flop your spins around with that term. And then there's this JZ term, which essentially just gives you an energy cost if they are both the same. Either up, down, either both up or both down, it's positive, and if they're different term states, it's negative or attractive. And now that's kind of the basic system. So the first question we now asked is, imagine the experimentalists could do all of that. Can we do something interesting playing with the interactions and the geometry? So we asked, imagine I put the system in 2D, can we use these interactions for something? And specifically, we were asking, can we robustly create entangled states due to these many body interactions? And to maybe phrase it in something that is more familiar to people here, essentially the question is, if I have many of these dipoles in a disordered system moving around, do I get a synchronization transition where all of these dipoles will behave collectively?
So I just curious, like, when you started with electric dipole, right?
Yeah.
Then you end up with a spin model.
Yeah.
Is it like to start with this magnetic dipole and then?
Right, you could also have done with magnetic dipoles. It would be the same, but then you don't get the JZ term that's tunable. So magnetic dipoles, of course, also exist, but they only have exchange interactions. They don't get a JZ term for free, and it's not tunable by electric fields. But there's other platform magnetic atoms that prove.
Sorry, my bad.
Yeah.
So
Yeah.
you neglect rotational degree of freedom.
I projected it down to two of them. So what we do is we apply an electric field which splits all levels, and then the scale of that degree of freedom is the largest scale. And the problem is like gigahertz, and anything else is low energy. So they will never change. Unless you initially do it. So you can say apply a laser pulse and put it into some of them, but once they're in there, they can only exchange that energy. They can't go to a different state anymore. Yeah, that's right. Right, and you can.
And in this case, you have the O3 model rather than this SU2, right?
It's an XXZ, so it's
Because the angular momentum go to 1 rather than 1/2.
it's 1/2, right? Because that's what we projected down in. It's a spin-half model, right? So we project into those two states. Of course, there's other states around, but this splitting is so large that you can never leave that manifold.
Okay.
So you forever stay in these two levels.
Okay.
Right. So I said the first important thing is that if you put them in 2D, you get this essentially what I would call here maybe a synchronization transition. And the second bit is that it allows you to robustly generate entangled state because they're all synchronized and behave collectively. And then briefly, the full Hamiltonian. So I told you, you have this rotation degree of freedom. I select two of them, I get a spin, a half. I put them in 2D in a harmonic oscillator, so there's motional degrees of freedom. And then I put those two together, then I have two oscillator states, one for the up degrees of freedom, one for the down degrees of freedom, and there's splittings between all of them. So the energy scales that now matter is the frequencies of the up spins, frequency of the down spins, which are generically different. So that might already give you an idea how that might also connect to Kuramoto models where there's frequencies that are different for all of these spins. And then the next bit will be interactions, and that's kind of the interesting bit. So what we are imagining is, imagine I take these dipoles and I put them onto sides of this synthetic lattice. So they all occupy motional states, which are now in x and y degrees of freedom. And then there will be exchange interactions between these dipoles that are kind of localized in this synthetic lattice. And if you do that, you have to make a few approximations to simplify the model a bit. So you have to neglect motional relaxation, and you need at most one particle per side, which you get for free in a Fermi gas. So that works. And we have to work in a regime where the mode changing polarizations are slower than the spin degree dynamics. And then you get a long range XXC model in mode space. So it's essentially the same model, just instead of real space coordinates are now a sum of our harmonic oscillator modes. And it's again an XXC model plus a local field term. And the physics is the same. The exchange term will again flip the spin degree of freedom of these molecules that are localized in mode space. And the GZ term will again give you energies. Now, why did I go through this hard work to project everything down into motional states? Essentially, what we do it because it makes the model way more collective. So what I'm comparing here is, imagine you would have put them in real space, which is this blue distribution, which shows you the strength of all pairwise interactions in the system. Sorry, this is the orange curve, and you see there's kind of a few very strong interactions if you're next to each other. They interact strongly, and then there's many molecules that are very far apart, and then they only interact very weakly. By putting them into harmonic oscillator states and letting them move around, kind of you average out that effect, and you get kind of this nicely, sharply peaked pairwise interaction function. And that will allow us to get a transition to collective behavior. So why do I kind of stress this collective behavior? So the first question is, what happens if you didn't have interactions? And then you only have this local Z term, which, as I said, comes from this difference of the mode frequencies, and it's inhomogeneous because it also scales linearly in the oscillator occupation number. So it's not quite a fully disordered model like in Kuramoto, but it's still non-linear.
So yet again, so in your model, you have this drop-in potential,
yeah,
right?
That's right.
And then you are considering the lowest band model.
Excuse me?
I mean, you are considering again this lowest band model, like this harmonic oscillator.
Yeah, it could be in any of these modes. Yeah. So there's a frequency for the downspin, and there's a different frequency for the upspins, and it could be in any X and Y of these motional states.
What about this mass effect? Like you are considering different mass, right? Different atom level.
Two different frequencies of the trapping potential. Yes.
And also this, I mean, in your molecule, these two atoms are different, right?
Sure, but they are bound very tightly, so that doesn't change. So you can think of that as a single particle. Yeah. So of course, there are also different masses, but they can't get apart, move apart. So they're always bound. So the binding length doesn't change at all during any of the dynamics. That's an energy scale that we don't touch at all. Yeah. So they are moving. Well, they're not even moving, but they are localized in these oscillator states as a single molecule. Right. And then what you would do is, say, imagine you kind of prepare all your quantum states, say, pointing along X, and you apply this Hamiltonian, and then you just get dephasing. So over time, all the spins essentially randomly dephase, and at the time it is linear and its frequency difference of order 1, you're completely dephased. So if you wanted to quantify that, you could ask, okay, how long is the total length of my spins? And initially, all of them point in the same direction, so it's n, extensive in the number of degrees of freedom you have, and after a time of order 1, that is 0. So that is the non-interacting case, and now you can ask what happens in the interactions. So what we find is essentially a dynamical phase transition that we could call a synchronization phase transition. Being a bit careful, so it's not a dynamical phase transition in the most strict sense. It is a dynamic phase transition in the sense that the dynamical behavior of the system changes abruptly as you change parameters. And the order parameter is just this length of the spin that I just defined. And we can look at the length of the spin over long times as a function of the interaction strength. And we essentially find 3 different regimes. There's kind of this regime C that I just showed, essentially non-interacting, that is just decays down to 0 very fast. This kind of intermediate regime where it kind of gets one oscillation and then kind of continuously going down. And then there's essentially a protected regime where this spin length stays essentially of order 1, infinitely long. In this case, we also include losses. So there's some decay because it's actually an open quantum system, but essentially it has fully synchronized. All the spins point in the same direction. And you can do this essentially as a function of this dephasing strength and the interaction strength, which we can tune by this electric field. And there's a nice phase transition here, it's dephasing, and here it's collectively protected. So this is now this dephasing transition we get. Now the question is, that's nice, we find this dynamical phase transition. Is there more interesting quantum dynamics that happens? Right, and similar things can also happen in other quantum systems. You can also do it with contact interactions and many other ways. So the next thing is what actually is the collective limit of this model. So what I now do is, instead of looking at the individual modes, I just average the whole model over all modes because it behaves very collectively. And what we then see is that essentially get a Hamiltonian that you might recognize. It's called one-axis twisting. So there's a term that just depends on the total spin length. That's a concept of motion, essentially. There's one interaction term, which is a C-square term. And then there's a global field, which is just an overall rotation, the collective limit, which also doesn't matter. And what does one-axis twisting do? So imagine you have a quantum state that points along X out of the plane. And then you kind of have a Z-Y noise. And initially, that's just Gaussian, it's square in half, and that's classically sensitive. If you apply one-axis twisting Hamiltonian of this form, what will happen is above the equator, you will kind of twist your state to the right, and below the equator, you will twist it to the left, which is strength, which is proportional to your distance. So instead of a circle, you will get an ellipse. And you can already see that this ellipse now has kind of a shorter and a longer axis. And intuitively, the shorter axis is now more sensitive. Because if I want to sense a rotation, I'm asking if I rotate this distribution, say over here, when can I distinguish that I actually rotated it? So this is now a more sensitive state, and you can quantify that in this way. And this essentially tells you how much the quantum entanglement makes the measurement better. And the corresponding parameter would be the Ramsey squeezing parameter, which just quantifies exactly what I described before. And you can also look at that as a function of time. What we see is that you kind of get quite a bit of squeezing. So we generate a highly entangled, metrologically useful state by these many body interactions.
Question.
Yeah.
So this is the numerical results?
Yeah, this is not numerical. Yeah. Yeah, so maybe I should have said how the numerical method actually works. So what we are using is a semi-classical phase space method, which is called discrete truncated Wigner. And for those that don't know, I think I was looking at the right stuff.
I think there is something here.
Right. So essentially what we do is, so imagine you have kind of one of these spins. So maybe
No, you have to
press
change.
the left. Look
down.
The menu, you choose the navigation.
okay, great.
Now
Yeah.
to-
Right. So essentially I have kind of this collection of spins, right? Many of them in some quantum state. And what we're doing is we evolve all of those in time via essentially like mean field equations of motion to some final state, right? There's some more upper spin degrees of freedom here. And what we're doing, so if I only did this would just be mean fields. It wouldn't give you anything. So what we do is we don't sample a single state, we sample quantum noise. So each of these states is kind of sampled, it kind of points in one direction, say along Z, but it could also partly point along X or Y. So essentially what we sample is for each spin state with one up, we sample 4 states, kind of one where it's essentially X, X, Z. And then we also sample all of these combinations of plus, minus 1. So for a state that, well, maybe points along Z, we sample all of these 8 states. So it could also point along X minus X or Y minus Y to get a quantum noise. And we sample it individually for all of these spins. And then we get a kind of a Monte Carlo simulation of this quantum spin system by adjusting mean field equations. And it turns out this is extremely good if you have collective systems that are somewhat mean field-like. You can also compute OTOX doing that and 2-time correlation functions. And it works remarkably well for many systems, way better than it should. And it's relatively easy. So that's actually how I came to do it. So I did classical spin systems before, and now I do classical spin systems with sampling, and it works for quantum spins, which I find very, very useful. Right. So this is the now robust transition where we get dynamical collective behavior, which then is also useful for quantum metrology. So that's kind of the main part of what we found here. So we kind of found this dynamic phase transition, we found this robust spin dynamics, and we got spin-free states. And of course, we could now ask, okay, can we do more? You could look at Botox, time reversal protocols, many body chaos in these systems, which hasn't been done yet. So that's things that might be interesting to do at some point. So this was, at this point, it's a proposal, so it's theory. And I kind of told you all of that is possible. And then we went to the experimentalists and asked them what they can do. So this is now the part is where the experimentalists show you that in principle, what I said might be feasible. I'm going to go through this part a bit quicker. So essentially, the main upshot of this is experimentalists can actually prepare two-dimensional systems of dipolar molecules. So just maybe explain you how that works is, so imagine you have these bilayers. So the idea is you have an optical lattice along one direction, which confines you into pancakes. And then you have these spin degrees of freedoms in them, which you get for free from the dipolar molecules. And what the experimentalists can do is they can apply an electric field gradient along the lattice direction, which then kind of gives you a detuning in these layers. And now, because you have energy selectivity, you can do whatever you want, essentially. I think that might be enough for this audience. So the point is, because I can translate energy difference in a spatially selective way, I get state control in a spatially selective fashion. So that's the main point of what they did here. And then you can kind of go through the details of the system. But the main point is they did it. It works. They can control that system. We can explain the measurements, and it works. Can also do a bit of theory to say how it works. So the main upshot is they can prepare these 2D systems, and we roughly know what happens. If I have a bit of time at the very end, I will kind of talk about interesting many body dynamics in this system, which they haven't studied yet. I want to briefly switch over to the second part of the talk, which is about Pauli-blocking. So this is a very different topic, but it is connected in the sense that it is again about dipolar long-range interactions. And the questions that we asked here is, well, first of all, can we observe Pauli-blocking in a physical system? So it might not everyone might know it's, I mean, everyone knows Pauli-blocking. You might have learned about that in your basic quantum mechanics course. You might not know that it actually had never been observed in a system until this year, in a bulk system. And then there's also an application question. So can we use that actually to engineer quantum states a bit longer? And why is it important? So for me personally, I think it's a very fundamental question. It's kind of fun to be able to find it in an experiment. Why is it interesting from a theory perspective? So what is really hard in this problem is that to understand it, you need to understand the interplay of quantum statistics in terms of Pauli-blocking, the motion of these quantum particles, and these long-range dipolar interactions that are induced by the light interacting with the internal states of the atom. So that's why it's a pretty hard problem. And we certainly didn't solve everything or even a lot, but we did manage to get to the point where we could actually propose experiments that turned out to demonstrate Pauli-blocking. So the basic kind of motivational part is, so every one of you knows spontaneous emission, which is kind of one of the most fundamental processes in light-matter interaction. So we have a two-level system. I place an atom in the excited state. After some time, it will just decay down on the emission of a photon. And that is what makes fireflies glow. It's also what laser diodes are kind of based on, and kind of pretty much all tools where we manipulate matter with light is based essentially on these kind of processes. The second thing that you might all know is, of course, quantum statistics. It is the Pauli principle, which just forbids two fermions to occupy the same quantum state. So you might have maybe learned about that as a statement about statics. So this seems essentially to constrain the distribution functions of fermions. In a sense, if I have a Fermi sea or Fermi system at 0 temperature, I will kind of occupy all states up to the Fermi energy and nothing else. But the interesting part in this project is that, of course, it also has consequences for dynamics. So imagine I have an excited Fermi sea and ground state Fermi seas, then the Pauli exclusion principle will limit the kind of dynamical processes that are allowed, because some of them will end up in an already occupied state, and some of them will end up in an empty state. So in that sense, Pauli-blocking also gives you dynamical constraints of what can happen in your system. And that is kind of what is at the heart of the process we want to observe. And to give a bit of background, how you might think of looking at it in an experimental system. So imagine I have kind of a Fermi sea that is kind of this large blue circle, and I kind of have lots of kind of atoms in here, and I shoot in a laser to excite this atom here. It will kind of jump over here as it absorbs that momentum, and then after some time it will want to decay, and that again, as it kind of emits this photon, it will kind of jump again with the same recoil momentum of the initially observed momentum. And then there's some transitions that will be outside the Fermi sea and some will be within the Fermi sea. And those will be fully blocked. So what you should see from that simple image is that you have a ground state Fermi sea and you kind of excite it with a laser. The emission of that from that system will be directional. And you will cover the internal and motional states of your system. So the signal should be directional emission and suppression only in certain directions. And that was observed last year by 3 groups for the first time. Of course, this is not the full story, right? So essentially what I'm telling you is, if you shoot a laser in an atomic cloud, there's a bit less light in some direction. But I promise you Pauli-blocking in some sense. So you could ask, can we actually observe the Pauli-blocking itself? And that's kind of what we did next. So the question is, can we really see that an atom lives longer? And that is significantly harder because to really see atoms live a long time, you want to excite many atoms, which then means you have a many-body system that you have to consider. And ideally, experimentally, you also want a transition that is slow, so you have enough time to actually look at the atoms while they are excited. And of course, if the transition is slow, then the time scale or the energy scale of the process is comparable to the interaction time scales and to the motional time scales. So really you have to understand all of those at the same time, which again makes it a complex question. And that's kind of what we set out to do. So this is a basic image of what the experimental system looks like. Again, it's kind of a 1D optical lattice with lots of pancakes. You shoot in a laser from below, and then you want to kind of excite these atoms with that laser, and then kind of count how many are in the excited state. In each of these pancakes, there's kind of fermions in this case, so they could be ground states or in excited states. Specifically, it's kind of 87 strontium because that's what they have in the lab. And it's a free-level structure. So the important thing for you here is that there's 2 ground states and 1 excited state. And because I shoot in light, it will be coupled by long range dipolar interactions. So that is the system you want to understand. Pauli-blocking dipolar interactions and motion in quantum degenerate Fermi gases. And that's what we then did. So the level structure is very useful for you to give you a bit more insight. So the point is that this transition is very weak and this transition is strong. So the basic idea is put atoms in both states, excite those to the up state, and then they will be very strongly blocked because all of these atoms will still be around, but those will be gone. So there will be a bit of decay, but it won't be as bad as in the case when you excite all of them. So that's kind of the goal. Now to get to the theory. So first of all, we have kind of motional states in the plane. For us, it will be simple plane waves to make it easy. We have the lights, so there will kind of be photons floating around everywhere. And then the interesting part is the atom-light coupling. And I talked about dipolar molecules before. They have long-range interactions because they're permanent dipole moments. It turns out that a multi-level system interacting with photons also gets dipole interactions. So if you kind of look at a photon master equation and you integrate out the light field, you get long-range dipole interactions between the excited and ground states in the system.
So with the polarization of the photon is important.
All of them. Yeah. So you write down the full master equation, including all polarizations. You integrate out the light field, and then you get the equation only for the atomic system.
So you read over the polarization rather than.
We sum over the polarizations, yeah. So essentially, right, of course, that's coupled, right? So the emission direction is, of course, coupled because the polarization has to be orthogonal to that. And there are, of course, constraints because we are in a 2D pancake. So, of course, if you want to emit out of plane, you have to get the kinetic kick into a Barnier function along that direction. So there are, of course, constraints, but essentially that's all properly included in the full model. So that's integrated out and then probably accounted for, yeah. And in principle, both polarizations matter. Of course, then if you were to absorb the light, then there's another coupling, but we don't observe the light at all. We only ask how many excited atoms are there. So our signal then doesn't depend on the polarization in that sense. Okay, then, right, we do the theory, and the basic understanding of what happens is, so this is a plot of the momentum space of my model. I have a large blue Fermi sea, I have a red Fermi sea, which are the atoms are excited. I will also choose that smaller than the ground state blocking Fermi sea, and then there will be kind of long range dipole interactions between these momentum modes that are induced by the photons. And again, that can be kind of boiled down in these pictures. So the basic idea is an excited atom can decay and excite a ground state atom. They can kind of flip their internal state. However, the important thing is that if they can decay, they can also exchange the momentum state, because there's this recoil kick. So by decaying, they will also decay to other states, which may or may not be blocked depending on whether there's an atom around. So again, there's a coupling with internal states and motion in this spontaneous decay process, which makes the system a bit harder to treat. And to give you a bit of physics, so these are the field equations. So what I'm looking at is the excited state population as a function of time. And there will be two terms. There will be Pauli-block decay. So this gamma is essentially the spontaneous decay rate from momentum state K to momentum state Q, which only happens if there is an excited atom in momentum K, and if there already is a ground state atom in momentum state K. So we get both Pauli-blocking of the spontaneous decay here, and then we get interactions terms. So those are essentially terms that you might know from super or subradiance, where the interactions that couple to the coherences between ground state and excited state can either lead to enhanced or suppressed decay rates. So those are cooperative interaction effects, and those are the terms that kind of make the model a lot harder, because if you want to measure a suppressed decay rate due to Pauli-blocking, you have to prove to me that it doesn't come from these terms. Because otherwise you've not measured Pauli-blocking, but subradiance, which you've known for a long time. And that is the basic idea how to do it. So you say we kind of have our two pancakes, two species. One will be a minority species. We're going to excite it to an excited state. And say for pi flip, the easiest one, we put them all up here. Then we wait for some time and we count how many excited atoms are left. And then we just fit a decay rate to that. And you can do it if you do the theory calculation. So what I'm looking at here is it possible at all to distinguish Pauli-blocking and cooperative effects? So I plot here the effective decay rate of my system as a function of the blocking species and the species that they excite. So over here, there are only a few atoms that excite, but many blocking atoms, which means I'm highly Pauli-blocked. And in this plot, I show the ratio of the interacting to the non-interacting model. So this tells you how important are interactions effects for my decay time. And again, if I go to the left corner where I only excite a few atoms, but have many blocking atoms, this ratio is 1. So if I were to do an experiment up here, then I know there shouldn't be any interaction effects, but I will see a lot of Pauli-blocking. And that's exactly what they did. So you can now look at the decay rate as a function of atom number, and you kind of see a clear suppression of about 25%, which roughly fits the theory within the errors we have. And you can also do the experiment as a function of this tilt angle, which controls the coherences, and again, it's perfectly flat as we predict. So this really tells you there's no interaction effects, and we have observed Pauli-blocking, which is kind of nice. And in principle, if you were to make it a bit cooler, you could also observe significantly more Pauli-blocking, which then means you could have gotten up to lifetimes that are twice as large as in free space. So what we did is the main contributions are we kind of developed this mass equation momentum space, which can get cooperative effects and Pauli-blocking. We proposed a situation where it should be observable, and they actually observed it. But this is kind of the Pauli-blocking part, which was the part where we kind of combined all of these 4 things that I discussed at the very beginning of my talk. I kind of talked about these internal states for dipolar systems to get spin degrees of freedom, and I talked about them in kind of strontium or SU and Fermi gases to get also dipole interactions. I told you how we can tune interactions either by light or by electric fields in dipolar molecules. And then I showed you different situations how we can exploit motion degrees of freedom, either to tune the type of interactions to become very collective, or to kind of have an interplay of interactions and motion in the case of spontaneous emission. And in the very last bit, I also included quantum statistics, which changed kind of the dynamics of what we saw. So this was all over kind of exploring 2D dipolar systems. the few projects I discussed. If I have a bit of time, I have a bit more time, right?
Yes.
Then I could talk a bit about kind of interesting many-body dynamics that I find even more exciting than what I've discussed so far. So going back to the case, they can prepare these bilayers. Another question is, are there interesting many-body physics in there? I should thank, I guess, my former supervisor and, of course, all the experimental people that did all the hard work for many of these projects. So again, our work, let me briefly look at what I can do in these multi-layer systems. So why should I do that? So the first thing is, if I actually put in a lattice, I can get rid of all of these losses, which is nice. I get a good spin model, so I'm now reducing complexity by throwing out motion completely. And I can hopefully get coherent many-body dynamics. These are the capabilities I discussed, so they can really prepare these bilayers, they can control the state in each of these layers individually, and they can prepare essentially any non-equilibrium state you want, and then look at what the dynamics is. And to go through one example that I kind of find very cute. So imagine you prepare one layer in an upspin and the other layer in a downspin. And then you ask, what does the exchange between the layers do? So essentially now mapping the dipolar exchange between layers onto creation operators or Holstein-Primakov bosons. And you will see is that the spin exchange gives you pair creation. So in some sense, you can consider the up state in the upper layer as a vacuum and the downspin lower layer as a vacuum. And if I do a spin exchange, then I create one excitation here, which is perfectly correlated to creating another excitation here. So I have perfect pair creation out of vacuum in these two layers. And that is kind of the process that happens in upper system results. It also happens in spinor BCs. It also happens in mode squeezing or in parametric amplification. It also happens in Unruh radiation, in general relativity. It's a very fundamental process that we want to explore in this kind of non-equilibrium setting. And this is maybe something that I want to skip. So maybe to look at something that I kind of find very interesting. Imagine you prepare not a single layer, but kind of many layers. So now this is a plot. Imagine kind of there's a layer here of many spins. There's another layer here, 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 here. So I really have a multi-layer system of many of these pancakes. And I prepare a state that is a non-coplanar spiral. So say the first layer, my spin points along x, then there's a spin that points along y, then a spin that points along z, x, y, z. And then you can ask, what is the many-body dynamics of the system? And you can map, first go to a rotating frame. Then you starting from a Heisenberg Hamiltonian, what you get in this rotated spiral is kind of a non-reciprocal coupling where x spins couple to z spins to the right, but well, so z spins, x spins will couple to y spins to the left. And if you then do Holstein-Primakov here, what you get is a bosonic coherent guitar, which is a non-dimensional Hamiltonian that has non-reciprocal couplings. So by using these dipole interactions to create a collective spin, then creating a non-coplanar spiral, I can realize a non-reciprocal non-Hermitian system. And you can also show that it works. So what I'm showing here is the Green's function of my lattice system as a function of distance from some central layer. And if they are red, then that means all the correlations that come from an X spin propagate to the right. And if it's blue, it means the correlation that propagated to the left came from a Y spin. So this Karel-Kitaev model shows perfect Karel transport, even in the full spin physics. So what I'm solving here is, again, the full spin dynamics of this dipolar multilayer, computing the Green's function, and seeing the predictions of the Karel bosonic Kitaev model in my spin model.
Sorry, I probably missed it.
Yeah.
But, you start from 2D layers?
Yeah, so each of these spins is a 2D layer. So there's kind of a 2D layer here, a 2D layer here, a 2D layer here. So each of those are very collective. So the point is, to do a Holstein-Primakov, you need a large spin. Typically, you don't get large spins in quantum systems, or you have maybe spin halves. So the idea is to use the dipole interactions to make them collective. As I showed at the very beginning, so you get a synchronization transition. And then you can use this very collective spin to play bosonic games. Yeah.
I'm sorry, then in which sense there is motion?
Right, the excitations. So it's a Holstein-Primakov transformation in the rotated frame.
So there is the spin 1?
No, it's a spin n, where n can be as large as the 2D layer. It can be 1,000.
I see.
Yeah.
So basically, it's possible.
Yeah. but it's very quantum bosonic. Yeah, but it becomes, of course, more classical, but there's still some quantum behavior in the sense that you get this, well, I guess you could get chiral transport also in purely classical systems, if you engineer it right, but you have to get the non-reciprocity into a classical system somehow. Of course, you could just write it down and say it's there, but here we get it, well, not for free, we get it by preparing a spiral, so we are cheating a bit, but in that rotated frame, we do get this nice chiral coupling. Yeah, we're kind of exploring that a bit further. You can kind of do more cool things there with the pair creation. But that was the last thing I wanted to talk about is multi-layers. It's also nice for squeezing. You also get too much squeezing in these systems. Yeah, let me go back to my summary. Right, maybe flashing that again. Other things have overlapped that I didn't have time to talk about at all. So I'm very happy to talk about any of those projects as well with anyone, of course. So yeah, I'm still around today. Contact me if you have any questions on what I talked about or on any of these projects. Yeah, and thank you for your attention.
Thank you, everyone, for the very nice talk. We still have plenty of time for questions, comments. Go ahead, yes, Andre.
You mentioned synchronization and the speeds, let's say, aligned to each other. Usually synchronization implies the presence of dissipation.
Right.
But somehow I don't.
Right. So it's not synchronization in the strictest sense. So what we are doing is we initially start all of them aligned, right? They're all pointing in the same direction initially, but we have disorder in their oscillation frequencies. So in some sense, we are just asking, does the dynamic stay in this collective regime, or does the disorder destroy that collective spin? So it's not like it's a limit cycle that will require dissipation. We are only asking, really, do we leave it or do we not leave it? So is it, I guess if you would think about it, equilibrium question, is it like maybe an actual minimum of some free energy so that we don't actually go away from it due to disorder? Yeah, but it's also never an infinite time question we are talking about. So in principle, all of these systems also have losses, so they will die out anyway. So it's really only a question about the time scale you care about for the time scale for whatever process you care about for the dipolar exchange. Does it stay collective enough for the time you care about?
Okay, more questions? Yes.
So you mentioned about this non-reciprocal engines.
Yeah.
Is it also possible to engineer within the same component like X and Y, non-reciprocal?
I mean, I skipped a few. So the thing is, generically, if you have any, well, so imagine it's purely classical, and they prepare this spiral state. Since the Heisenberg Hamiltonian is generically, imagine you have a nearest neighbor Heisenberg model of these large classical spins. Most initial states are purely chaotic. It turns out that this is the only non-trivial initial state that is exactly solvable. So it turns out for this one, you can solve the mean field dynamics exactly, which I only know the fully aligned states that just don't have any motion. It turns out this one has dynamical motion and is exactly solvable, which I'm not sure if people knew before, but that's true. So if I wanted to engineer something more generic, I would imagine you end up in a situation where your initial state is not a classically stable or dynamically stable state. So you might just get chaotic dynamics potentially. But that doesn't mean that you can't do it. It might just need someone smarter to figure out how to engineer it specifically. So in this case, we kind of do rely on this kind of period-free periodicity, which I guess is the reason why it ends up being stable. If you wanted to individually only do X or Y couplings, well, I guess in some sense, after you hold some Primakov, it doesn't really matter because there's really only two directions anyway. There's only X, Y, there is no Z because you project onto the plane orthogonal to your spin direction. So you would want so in that language, what would you actually want to engineer? But yeah, I'm not saying that's impossible. You could imagine doing further twists. You could also not start from a Heisenberg model. So we start from a Heisenberg model because that's the easiest case. But of course, you could start with different couplings. You could have different ZZ to XX and YY couplings and play with that for sure. The problem, of course, is if you do a spiral and you don't have full SO3 symmetry of your model, then where you put your spiral matters. In this case, it didn't matter where I started my initial state because it was fully symmetric. It would if you don't have that symmetry anymore.
Okay, more questions? Doesn't seem to be the case. So let's thank Thomas again. Thank you very much.